Hello everyone and welcome back. I'm Mahnoor and today we will be continuing on with the chapter of dynamics specifically for AS level physics. Now up to this point we have covered essentially Newton's first law of motion, and let us quickly recall what we had discussed over there. When we were talking about Newton's first law of motion, we had basically described it as follows, that an object will stay at rest or will maintain its state of rest or motion with constant velocity when the resultant force acting on that object is 0 newtons. And we had explained from this first law that this property of an object to be able to maintain its state of rest or motion with constant velocity implies that there is this tendency that objects have that they can resist any changes in their motion. And that was where we had talked about inertia. And there we had, not only had we defined inertia as this built-in property that allows objects to resist changes in their motion, but we had also introduced this notion where we related inertia with its mass, and we saw how the more mass an object has, the more ability it has to resist changes in its motion, and vice versa. So we saw how mass was a physical representation of inertia, right? Now, with all of this aside, we want to bring back something that we had introduced in our previous lesson regarding forces. There you may remember that when we were studying ways of conducting vector addition with forces, we had seen how we could basically add up one or two or more than two forces by seeing whether they're arranged in the same direction or in the opposite direction, right? Now, I want to bring back the first two examples that we had done in that previous class. So let's cut off our discussion here and let me recall what we had done last time. I repeat, we recall that during vector addition of forces, we had concluded the following, that if, let's say, I have an object that has forces acting in the same direction F1 and F2, we recall that we would combine these two to give the resultant force as F1 plus F2 since they're in the same direction. And in contrast, we had seen how if we had the same object but this time forces were arranged in the opposite direction, depending on which force is larger or which force is smaller, we would be subtracting the two forces. So it would either be this or F1 minus F2 or F2 minus F1. Now, you may even remember that we had related this to some physical aspects as well. More specifically, we had seen that when two forces add together, we saw that as a physical effect in the fact that the object would speed up. Whereas, in the second scenario where two forces are acting in the opposite direction, we saw an effect of the object slowing down. Now, while yes, these two are different scenarios, what is shared between the two is the thing that their resultant forces are anything but zero. So what this shows is that whenever the resultant force is non-zero, what that means is that the object will either speed up or slow down. Object will speed up or slow down. When we say that an object is speeding up or slowing down, what we mean to say is that that object's velocity changes. So I can take the same statement and rephrase it as follows. I can rephrase it and say that when the resultant force is anything but zero, that means that the object, or rather the object's velocity is changing. And you may remember from our discussion in kinematics that wherever there's some changing velocity that exists, that means that there is non-zero acceleration that is also present. So we repeat that wherever velocity is changing, acceleration is most definitely present. So then we conclude something quite fundamental when it comes to the scenario where the resultant force is not zero. That is, that when the resultant force is not zero, it leads to an acceleration. What I've presented here as this statement, this is an extremely important statement, so much so that it follows Newton's first law into what we call Newton's second law of motion. So let us define that first. We're now entering Newton's second law of motion. And we formally phrase it as follows, that when the resultant force acting on an object is non-zero, that is, when the resultant force acting on an object is non-zero, that means that the object will accelerate in the direction of the force, or rather the resultant force. Of the resultant force. Not only does this law state that it is non-zero resultant force will lead to an acceleration, but moreover, this law also relates with it the numerical way in which the resultant force relates with acceleration. It is related using the formula mass times acceleration. So this is our formula. M represents mass that has to be expressed in the SI units of kilograms. A is acceleration that has to be expressed in SI units of meters per second square. And then the resultant force is Fr, resultant force, which will obviously be in newtons. Now, when we have this expression, it's very important to note a few things regarding this equation. First and foremost, that acceleration is never related to just one individual force or the other. If you have more than one number of forces acting on an object, then you have to account for its resultant value first before you can begin using this expression. Hence, there is an emphasis on the fact that this law only works when you have the resultant force at hand rather than just one individual force or the other. So this point we should keep in mind, especially when it comes to questions where you have more than one kind of force acting on an object. So that's the first thing. Now, in regards to this, we can actually relate this to the previous scenario. In the previous scenario, we had seen two kinds of resultant forces, right? We had seen an additive effect where the object would speed up and a slowing down effect where the object would slow down. This tells us that you can have two kinds of accelerations that can be represented over here. So, wherever the object is speeding up, that means its acceleration is positive, as we recall from kinematics. And where the object is slowing down, that means the object's acceleration is negative, which means the object is decelerating. So this brings an important point over here, that when the resultant force is additive, there will be a speeding up effect, and wherever the resultant force is reductive, there's a cancellation sort of an effect. That is where deceleration will occur. So that is something that is worth summarizing over here, that when the resultant force is additive, there will be acceleration that's present such that it's positive, translating as the effect that there will be the object will be speeding up. And on the other hand, when the resultant force is it has a cancellation effect. Let me phrase it that way. Has a cancellation effect. That means acceleration is not positive but rather negative. That would mean that you have deceleration involved this time. So deceleration is present this time, meaning acceleration is going to be negative. The next thing we see is that although resultant force and acceleration are definitely related with each other, not only is that relation present in terms of the magnitude itself, as far as the equation goes, but it also is related in the direction, in that the acceleration will always be directed in the direction of the resultant force. So if you have, let's say, this object whose resultant force points towards the right, it's natural to assume that its acceleration will also point towards the right. And in contrast, if you have the same object that has a resultant force towards the left, then its acceleration will match that same direction. So this just goes to show that acceleration and resultant force will follow the same directions no matter what. Now finally, we want to address this mass that we see appear here. If you think about it, for most objects that we consider, we'll be considering constant masses. So this tells you that for an object with constant mass, the resultant force and acceleration happen to be proportional to each other. So let's summarize that too. For an object with constant mass, meaning you can treat the term m as a constant, then you can take Newton's second law and take the constant and the equality sign out and replace it with the proportionality sign, meaning the resultant force and acceleration are directly proportional to each other. And if you think about it physically, it makes sense, right? Because if the object were to, if for example you had an object, let's say the same box, and you were to apply a resultant force that amounts to about, let's say, 10 newtons. And let's say it's 1 kilograms worth of mass, so its acceleration would be the resultant force divided by its mass, 10 meters per second square. Now if you take the same object and apply a larger force on it, so suppose now that resultant force is 20 newtons instead of 10, then the acceleration would be 20 over the same 1 kg, and you get 20 meters per second square. So see how for the same value of mass, if you were to increase the resultant force, you're definitely increasing the acceleration. And you can imagine the inverse scenario as well, that if you exert less of a force, the object won't speed up as fast as before. So it makes natural sense why for an object with constant mass, the resultant force and acceleration will be definitely directly proportional to each other. So with all of this out of the way, let us now conduct a simple sort of an analysis with a simple, like an applied question. So suppose you have the following kind of question. Suppose you have this box that has a mass of 10 kgs. And let's say here's Tufel, who applies a force of 10 newtons, and then here's Dr. Sal standing right behind him, applying an additional force on the same mass, and let's say that force is about, let's say, 50 newtons. And in all of this, suppose there is another friend of theirs who is applying a force in the opposite direction of about 5 newtons. And here in this scenario, we are asked about the acceleration. So in other words, you have 3 forces acting on this box of mass 10 kgs, and you're asked to find the object's acceleration. Now in this scenario, our immediate thought is to resort to Newton's second law, right? So we will keep in mind that we'd be using Newton's second law. Take that as a guess. Now with this guess in mind, I want you to pause this video for a moment, give this question a try, figure out a value for acceleration, and then after you're done attempting this, let's solve this together, okay? Starting now. You're done? Well, let's now attempt this together. Now, when I use this hint to my advantage of using Newton's second law, I'm reminding myself that, okay, I will use that the resultant force is mass times acceleration. But then I remember that I can't use just any one of these forces of 50 or 10 or 5 newtons. I need to consider a resultant value. Which means I have to, before I even use Newton's second law, I have to first combine these forces of 50, 10 and 5 newtons by figuring out that resultant value. Only then can I use Newton's second law. So let's do that step first. Now, according to the way I write, or let me put it this way. In order for me to combine these forces, I have to take into account their directions as well as their magnitudes, right? And we recall, in fact, I'll recall that before I calculate it, is that forces in the same direction, I add them, and forces in the opposite direction, I subtract them. With this in mind, if we go back to the diagram given, I can see how Dr. Sal's force of 50 newtons and Tuffel's 10 newtons both are directed in the same direction. So I can definitely add them together. So I can write that as 50 plus 10 newtons. But then I have the 5 newtons that is arranged in the opposite direction. Opposite specifically to 50 and 10 newtons combined. So after having added 50 and 10, I can definitely subtract the 5 newtons, and now it's just a matter of me simplifying. So I get 60 minus 5, 55 newtons. Now that I figured out the resultant force, now I'm ready to calculate the acceleration. It's just a matter of me rearranging Newton's second law to make acceleration the subject of the formula. That will require me to divide both sides by mass. So I get resultant force divided by mass equals acceleration. So now I just have to plug in the numbers, and I get 55 newtons divided by the mass of 10 kgs, and I get 5.5 meters per second square. Now notice how this is a positive value. So this means that even though there is a resistive force of 5 newtons acting on this 10 kg object, by resistive I simply mean it's in the opposite direction, even though that force is acting there, the object is still speeding up because acceleration is positive. The object will definitely speed up. Right? So even though there can be scenarios where even though there is a resistive force, there may be a scenario where the overall acceleration is positive, and so the object continues to speed up no matter what. Right? Alright, so that wraps it up for Newton's second law. In our next lecture, we will dive into Newton's third law of motion and understand some of its own intricacies, especially in how they relate with our universe. Before we wrap things up though, let's quickly summarize it. In our previous lesson, we had introduced Newton's first law, wherein we discussed that an object will maintain its state of rest or motion with constant velocity when the resultant force is zero. In Newton's second law, we were able to introduce the scenario of what happens when the resultant force is non-zero. There we discussed that the object will accelerate in the direction of the resultant force in accordance with the equation of resultant force equaling mass times acceleration. From this, we were able to identify that when there is an additive effect of resultant force, that will give you a positive acceleration, meaning the object will speed up. And wherever there is a cancelling sort of an effect, it may lead to the acceleration being negative, meaning the object will slow down due to its deceleration. Then we saw how acceleration and resultant force always are arranged in the same direction, and for an object with constant mass, the resultant force and acceleration are directly proportional to each other. So that's all for today. Thank you for your time.